Before we dive into the specific methods, let's be very clear about what scientists mean by backward time travel. This is not about daydreaming or remembering a fond memory. It is not like watching an old home video. In physics, traveling to the past means your physical body, made of atoms and energy, would actually arrive at a moment in time that has already happened. You would exist in a year or a day before the moment you started your journey. You could, in theory, step out of your time machine and breathe the air of a bygone era. This is a very precise and very difficult thing to achieve. The idea might sound like it belongs only in fiction, but it has roots in serious science. Our best theory of gravity, Einstein's general theory of relativity, is the main source for these ideas. Einstein showed that space and time are not separate things. They are woven together into a single fabric called spacetime. He also showed that massive objects, like planets and stars, can bend and warp this fabric. It is this bending of spacetime that we feel as gravity. The most famous and talked about idea for time travel involves something called a wormhole. A wormhole is a theoretical shortcut through spacetime. Imagine spacetime is a giant sheet of paper. To get from one side to the other, you would normally have to travel all the way across the surface. But what if you could poke a hole in the paper and tunnel directly through to the other side? That tunnel would be like a wormhole. It would connect two different points in space. It could also connect two different points in time, creating a bridge between them. The basic idea for a wormhole time machine is simple. You would need to find or create a stable wormhole. This wormhole would have two mouths or openings. Call one mouth A, call the other mouth B. At the beginning, both mouths exist in the same time. Now take mouth B on a special trip. Fly it around in a spaceship at nearly the speed of light. Then bring it back, or place it near a very massive object. For example, a neutron star with extreme gravity. Both of those actions cause time to slow down. According to Einstein's relativity, a clock near mouth B would tick slower than a clock near mouth A. If you left mouth A on Earth and mouth B went on a 10-year journey, time would pass differently for them. From Earth's perspective, 10 years might pass for mouth A, but for mouth B, maybe only 1 year passes. Now the two mouths are out of sync. Mouth A is 9 years ahead of mouth B. That time difference is the key. Enter mouth A in the year 2040. You travel through the wormhole tunnel. You exit from mouth B. Because mouth B is 9 years behind, you step out in the year 2031. You have traveled 9 years into the past. By going back and forth through the wormhole, you can move freely within that 9-year window. You have created a closed time-like curve, a pathway that loops back on itself in time. The idea of wormholes comes directly from the mathematics of Einstein's general theory of relativity. The equations that describe the shape of spacetime allow for solutions that look like tunnels. These are often called Einstein-Rosen bridges. Furthermore, the idea that time slows down is a proven fact at high speeds in strong gravity. This effect, called time dilation, is tested every day. The GPS satellites that orbit Earth have to adjust their clocks constantly to account for it. The biggest problem is that any normal wormhole would be incredibly unstable. The moment it formed, it would collapse so quickly that not even a single particle of light could pass through. To keep a wormhole open long enough for something to travel through it, you would need to prop it open with a special kind of material. Scientists call this exotic matter. This isn't just matter that is rare or strange. It must have a very specific property: negative energy density. This means it would have to weigh less than nothing. It would push space-time apart instead of pulling it together like normal gravity does. Do we have any evidence for this exotic matter? In the quantum world, scientists have observed tiny, fleeting effects that produce a sort of negative energy. This is known as the Casimir effect. However, we have only seen it in very small amounts and for very short times. We have no idea how to gather or create a large, stable amount of exotic matter needed to hold a wormhole open. Without it, a wormhole is just a fleeting mathematical curiosity. It would be like a soap bubble that pops the instant it forms, making it useless as a tunnel. To test this idea, we would first need to find a wormhole. Astronomers are searching for the strange gravitational effects that a wormhole mouth might have on nearby stars and light. If we found one, we would then need to figure out if it is stable. And to truly understand if it could become a time machine, we would need a complete theory of quantum gravity. This theory would combine Einstein's ideas with quantum mechanics. It would tell us if quantum effects would destroy the wormhole as soon as it was about to become a time machine. For now, wormholes remain a fascinating but purely theoretical concept. Another path to the past also comes from Einstein's theory, but it takes a different approach. Instead of creating a shortcut tunnel, this idea involves the shape of the entire universe. In the 1940s, a brilliant logician named Kurt Gödel found a shocking solution to Einstein's equations. He imagined a universe that was rotating. In this Gödel universe, the fabric of spacetime itself is being dragged along by the cosmic spin. This twisting of spacetime has a bizarre consequence. It makes time travel to the past possible without any wormholes. In this spinning universe, if you were to travel on a large enough path, you could, arrive back at your starting point before you even left. The rotation of spacetime would tilt your future light cone, the boundary of all possible future events, so much that it would eventually loop back and intersect with your past. It's a bit like running on a circular track that is also tilted. If the tilt is extreme enough, your path could lead you downhill in time, even as you move forward in space. You would simply be following a perfectly normal path through a very abnormally shaped universe. A more local version of this idea was proposed by the physicist Frank Tipler in the 1970s. He showed that you might not need the entire universe to be rotating. Instead, you could create a similar effect with a single, massive object. This object, known as a Tipler cylinder, would have to be incredibly long, theoretically infinite in length. It would also need to be unbelievably dense, and it would have to spin on its axis at a speed approaching the speed of light. The rapid rotation of this massive cylinder would drag spacetime around with it. If you were to fly your spaceship in a spiral path around this spinning cylinder, you could find yourself on a closed, time-like curve. It would be like finding a whirlpool in the river of time and riding its current backwards. The science behind these ideas is solid. In a mathematical sense, both the Gödel universe and the Tipler cylinder are exact, valid solutions to Einstein's field equations. Gödel universe, spinning cosmos solution. Tipler cylinder, spinning massive cylinder solution. They prove, in principle, that spacetime can be arranged to allow closed time-like curves. Under extreme conditions, those curves permit paths into the past. This is a profound discovery. Causality, the idea that causes come before effects, might not be a fundamental law. It could be a feature of how our universe is shaped. First, the Gödel universe. Observations suggest our universe is not rotating. Instead, it expands uniformly in all directions. That picture is very different from Gödel's spinning cosmos. Maybe there's a tiny, undetected rotation, but it's far too small to produce time loops. So Gödel's universe is possible on paper, but unlikely ours. Next, the Tipler cylinder. It must be infinitely long. Nothing we see is infinite. Even an extremely long cylinder still faces impossible requirements. You'd need to gather a huge amount of matter far denser than anything we know, and spin it at mind-boggling speed. The forces would tear known materials apart. Building one is beyond any conceivable civilization. It's a thought experiment, not engineering. How to test these ideas? Measure the universe on the largest scales. Search for cosmic rotation. All CMB data, the leftover heat from the Big Bang, shows no sign. For Tipler, look for natural analogs. The answer so far is no. Neutron stars spin fast and are dense. They are not long cylinders. They don't spin fast enough to make time loops. These remain proofs of principle, disconnected from physical reality. Our third possible path to the past involves some of the most exotic and speculative objects in theoretical physics. Cosmic strings. These are not strings like the ones you tie a box with. Cosmic strings, if they exist, are incredibly thin but unbelievably dense defects in the fabric of space-time itself. Some theories of the early universe predict that these strings might have formed as the universe cooled down after the Big Bang. They would be like cracks forming in ice as it freezes. These strings would stretch across vast distances of space and contain enormous amounts of energy and mass. The time travel idea involving cosmic strings is a bit complicated. It requires not just one, but two of these strings. The space around a single straight cosmic string is flat, but has a chunk missing, like a slice has been taken out of a pizza. This creates what is called a conical geometry. It does not, by itself, create a time loop. However, if two strings zoom past each other in just the right way, the space-time warping becomes much more extreme. The combined gravitational field could create a region where closed, time-like curves are possible. A spaceship that could fly into this region and loop around the two strings in a specific pattern might find itself returning to its starting point at an earlier time. The window for time travel would only exist while the strings were close to each other. The major problem with this idea is that we have absolutely no confirmed evidence that cosmic strings exist. They are a prediction of some theories in particle physics, but not all of them. Astronomers have been searching for the unique gravitational effects of cosmic strings, such as the way they would bend the light from distant galaxies, but so far, they have found nothing conclusive. Even if they do exist, the chance of two of them passing each other at high speed in just the right configuration to create time loops would be extraordinarily rare. It's not something we could build or control. We would have to be lucky enough to find it happening naturally. We have explored 4 of the most realistic paths to the past that physics allows. Wormholes offer a shortcut through time, but require non-existent exotic matter. Rotating universes could twist time into a loop, but they don't seem to exist. Cylinders could twist time into a loop, but they don't seem to exist. Cosmic strings might create temporary time machines, but they remain undiscovered. Quantum retrocausality hints at a two-way flow of time, but can't send messages or people. Each path starts with solid science, but hits enormous roadblocks. For now, backward time travel is theoretical, not practical. The challenges are not just technological, they're fundamental. The universe seems to have placed very high barriers against violating cause and effect. Stephen Hawking's chronology protection conjecture suggests unknown laws prevent paradoxes. The absence of time tourists from the future is strong, though not conclusive evidence. So, what would it take to move this field forward? First, a complete and verified theory of quantum gravity. Second, observational evidence. Finding a real, stable wormhole would change everything. Finding a cosmic string would change everything. Third, experimental breakthroughs, creating and controlling stable negative energy in a lab. Even if we never build a time machine, the quest is incredibly valuable. Pushing our theories teaches us about space, time, matter, energy. The universe is full of mysteries. The puzzle of time is one of the greatest. Perhaps a future breakthrough will provide a surprising new answer. Until then, we can look up at the stars and wonder. The search is its own reward. If you enjoyed this exploration, like and subscribe. Let me know in the comments what deep science topics you'd like next.